For this problem, on the topic of Coulomb's law, we are told that two small non-conducting spheres have a total charge of 90 microcoulombs. When the two spheres are placed a given distance apart, then we are given the force that each exerts on each other, and we are told that this force is repulsive. We want to calculate the charge on each sphere. We then want to redo the calculation if the force had to now become attractive. So if the force is repulsive, then both charges must be positive, since the total charge is positive. So if we call the total charge Q, then Q1 plus Q2 is equal to the total charge Q. And we know that the force between the two charges is K Q1 Q2 over the distance separating them squared, d squared. And we can write this as K into Q1 multiplied by Q2, which is Q minus Q1, all over d squared. So this implies that with some rearranging, we get Q1 squared minus Q times Q1 plus F d squared over K is equal to 0. So essentially we have a quadratic equation in Q. So if we use the quadratic formula and we solve this quadratic equation, we get Q1 to be equal to Q plus or minus the square root of Q squared minus 4 times F d squared over K. And this is all divided by 2. So now we can substitute our values in here, and we can find this value for Q1. So that's a half. And since all our values are in SI units, we'll suppress the units here. And this is 90 times 10 to the minus 6, and that's coulombs, plus or minus the square root of 90 times 10 to the minus 6 minus 4 multiplied by the force 12 newtons times the separation distance between the spheres, 0.28 meters, and that's squared, divided by K, which is 8.988 times 10 to the 9 Newton meter squared per Coulomb squared. So we will just suppress the units. We have SI units for all our values. So if we calculate this, we therefore get a value for Q1 and Q2. So we get Q1 to be 88.8 times 10 to the minus 6 coulombs. And so obviously from there we can see that Q2 is 90 minus this value. And the second charge has magnitude 1.2 times 10 to the minus 6 coulombs. So if the force between the two spheres is repulsive, these are the two charges on each sphere. Now, what happens if this force was attractive? Well, if the force is attractive, then the charges are of opposite sign, and the value used for F must then be negative. And other than that, we'll use the same method as above. So again, we write Q1 as Q plus or minus the square root of Q squared minus 4 times FD squared over K, all divided by 2. And as we did before, we'll put in our values and suppress the units. So that's a half into 90 times 10 to the minus 6 coulombs, plus or minus the square root of q squared, which is 90, times 10 to the minus 6 squared, so that as well in the first expression is 90 times 10 to the minus 6 all squared, and this is minus 4, and now the force is minus 12 newtons times the separation distance, which is still 0.28 meters all squared, divided by the constant k, which we know is 8.988 times 10 to the 9 in SI units. And so if we calculate, we get Q1 to be 91.1 times 10 to the minus 6 coulombs. And this is positive, so therefore the charge on Q2 must be negative, and this will be minus 1.1 times 10 to the minus 6 coulombs. So that's the charge on each sphere if the force between them is now attractive.